So let's see what's the evolution of a universe dominated by dark energy would be. Cancel the terms proportional to matter and radiation, and you have this equation. Consider also that the universe is flat. So you have, solve this for A. So we find that if the universe is dominated by dark energy, it starts to expand exponentially with the time scale given by square root of 3 over lambda c squared. And we can also define the density of dark energy in terms of the critical density of the universe. So that omega lambda is equal to the density of dark energy over the critical density, which is then lambda c squared over 3h cubed. We can then finally write the Friedman equation in compact form, including dark energy, as h squared 1 minus omega, a squared is equal to minus kc squared, with omega given by omega of matter plus the omega of radiation plus the omega of dark energy. And given the observations, the best model that fits the observations is omega lambda of about 0.7. So our best model for the evolution of the universe is given by the Friedman equation as with k very close to 0, omega matter is about 0.27, omega of radiation is about 8.24 times 10 to the minus 5, and omega of dark energy is 0.73. Now, if the densities fall as matter as 8 to the minus 3 and dark energy constant, then you can equate them to see when was it that the universe had an equal amount of dark energy and equal amount of matter. What is the scale factor that this transition corresponds to? Well, just solving this equation, energy of dark matter equal to energy of matter, gives you then A is equal to the scale factor of the transition matter to dark energy. So that gives you then 0.27 over 0.73, the square root of this, gives you 0.72. So scale factor 0.72 corresponds to redshift 0.39, or about 5 billion years ago. So 5 billion years ago, the universe had the same amount of dark energy and matter. Dark energy has just been increasing since. So that's the model that we have then. We have that 72% of the density of the universe is dark energy, 23% is dark matter, and the rest of it is atoms. Here you have a slice of the non-dark energy component. You have dark matter being then 63%, atoms about 12%, photons 15%, and neutrinos about 10%. It's disconcerting that the visible matter is so small. The matter that is luminous, the one that we can measure. So this is an illustration of this model. I like this illustration because it shows how little is it that we see. What we see is the luminous matter, as if this luminous matter were just beacons on the masses of ships that are on an ocean. The beacon of light is a visible matter. The ship itself is dark matter. And the ocean that they're going is the ocean of dark energy, about 70% of the universe. Now, the presence of dark energy also pushes the age of the universe a little further back. Since about 5 billion years ago, the universe has been expanding exponentially. Then it pushes the Big Bang a little further back to about 14 billion years.